And there's been a lot of talk about restoring degraded soils, and this is one of the targets for the IPCC and also for just improving agricultural productivity. But then the question is, how do you do it? And where are they? So our next speaker is Cheryl Palm, who is an ecologist and soil scientist at the Earth Institute at Columbia University. There is probably nobody on the planet who knows more about degraded soils in Africa. And so, well, maybe the only competitor might be Pedro. So, Cheryl, why don't you come and tell us, give us some reality.
Well, good morning, everyone. Canola gave a very good introduction into what I'm going to be approaching about. We talk about the processes for getting carbon into soil. I'm going to talk about some of the management practices for getting carbon into soil. To mention very broadly, I'll try to get a bit more specific. And I'm going to focus on Africa. So the approach I'm going to take is you have to look what is the actual carbon storage potential of a system. And that depends on climate, it can be rainfall patterns, and temperature. And when you're considering the soils, it really depends on the texture of the soil, if it's sandy or clay, the mineralogy, and also the depth of the soil. You also have to, as Dr. Lau said, how much soil's already been lost, or how much carbon's already been lost from that soil, and why, and then what can be done to rebuild it. And next, I'm going to try to deal with the issue of widespread adoption. We've talked about that a few times, but I like to bring up some of the challenges. And then the big question is, where has that carbon been lost? Where are these soils degraded? And how extensive are these areas where we might apply some of these technologies for getting carbon back into them? The focus on Africa and the challenges for getting carbon back into the soil are different in different places. I'm just picking Africa. We could talk about each place. But I'm doing it because of food security issues, and they cannot be compromised by getting soil back into the carbon. The huge biofuel discussions often don't consider where the food is being grown, where it should be grown. And so that's why I'm going to focus on that particular region. Just to give an example of what potential carbon storage is, this is a graph of the above-ground carbon, so that's vegetation carbon, in a range of natural ecosystems in Africa. And the below-ground carbon, this is being the topsoil, 0 to 20 centimeters, and this is 20 to 50 centimeters in the subsoil. So you can see it's hugely different. Africa's very different. Every place is different. Where you have 250 tons of carbon in a rainforest in Cameroon, but only about 50 tons of carbon in the subsoil, or in the first 50 centimeters. You go to Kenya, which is subhumid. There's less in the vegetation, but there's a lot more in the soil. It has to do with the clay mineralogy and the amount of clay, and so on. Then you go to the drier woodland areas, Zimbabwe, Miombo woodland, less than 20 tons of carbon above ground. Some Miombo woodlands have up to 100. So it really depends where you are in Africa, how much carbon you could actually store in that system. This is just a general diagram. If we then start to cut a forest for agriculture, you go through various things, slash and burn. You lose carbon from the vegetation and the soil. There are various management. But as your time increases, population, you sooner or later end up into annual cropping, row crop agriculture, bare soils. Bare soils expose the soils to erosion, more decomposition, and you end up with a very low state of carbon in all of these cases. There are various types of soil degradation. It's also very important to know what kind it is, and we saw some examples from Dr. Lau again. Water and wind erosion. You lose a lot of your fertile topsoil. You can also have extreme gully formation. Chemical degradation, that's the loss of nutrients, as Pedro talked about nutrient depletion in Africa. It's also accompanied with loss of soil organic matter. Salinization, acidification, pollution, physical degradation, compaction, crusting. Now, I'm going to talk mostly about the three that are circled because those can be approached in different crop management strategies, soil management strategies. You can increase carbon and you can also address food security. All right, just some examples. This is extreme water erosion. This is about a 50% slope in the highlands of Uganda. This is caught in the middle of a rainstorm. That is a farm. You see no physical barriers, or very few. And you can just see the erosion coming right through that crop. If you put fertilizer up there, it's going to end up down there. That's why people don't use it there, one of the reasons. Soil nutrient depletion, very poor crop growth, as Pedro has shown. Surface sealing is very common in semi-arid tropics. And so the surface seals, cementation, you have a hard time getting seeds to germinate and all sorts of things. And this, it can happen from grazing, all sorts of things. And here's compaction from a plow layer done by oxen, that they also have in there. These people could not even get a soil auger into the soil. So soil degradation takes many forms, and it's very important to know that to decide what kind of interventions. So here's the question. If we are now in much of Africa at this very low state of soil organic matter, what can we do to increase that carbon? So there are different ways to rehabilitate soils. If a physical property is there, that usually has to be the first thing you have to do. You have to physically protect that soil, either by building terraces to stop erosion or somehow breaking a plow layer and things like that. You also have biological and chemical rehabilitation. You usually have to do all of them. All right? It includes plants and soil organisms, a biological part, stone terraces, check dams, nutrients, and organic inputs. And you can do it at various levels. Very often we're just talking about plot levels, but sometimes whole farms or even whole landscapes are degraded. And so there are various ways to protect and rehabilitate those soils. So I'm going to talk about, as I said, ones for food production and also carbon sequestration. Here's just some examples of physical rehabilitation. This is in Ethiopia, where there's hardly any topsoil left in many parts of northern Ethiopia. It's just washed away. Fortunately, they have a lot of rocks, so they have a natural resource to be able to stop water erosion and soil erosion. Here's another example from Ethiopia where large gullies have formed from water rushing down the hills, and you have to physically stop that water. These are very fertile areas, but if you don't protect the gullies or stop the gullies, you lose all that. Then there are terraces, other types of terraces where you don't have rocks. This is a fodder grass that really stops erosion, and this is a tree that also can stop erosion. So there are all different ways you can physically rehabilitate soils. I'm going to concentrate more now on the biological and the chemical rehabilitation. And yesterday it was sort of, well, mineral fertilizers or organics. But you have to do both. And in Africa, you really have to jumpstart many of these systems because there's not even enough organics growing to do it organically. And that's a very important point. Some systems are so degraded that there is not enough fodder to produce manure. So you can't start with manure because you don't have livestock. The manure you do have is very poor because of the poor quality of any organic that's growing there. We've actually seen manure applications decrease crop yields because of the very poor quality of that manure. So remember where we're starting. We're at the very bottom of that curve. You have to add mineral fertilizers, certainly in the short term to get it going. But then you also have to add organics to get the soil organic matter going at the same time. Just examples here, people talk about legume cover crops. There are huge projects all over West Africa and some in East and Southern Africa. Biomass transfer, and this is in situ, as Pedro said, You grow the organic in place, it fixes nitrogen, and you incorporate it or just have it as a mulch. Biomass transfer, you grow the biomass off-site and you carry it on. That's the same as you do with crop residues or manures. And then improved legume fallows. It's like a cover crop, but it's a tree. And you can do this in about 18 months. So there are different ways to do organics and do organics plus mineral fertilizers at the same time. I'll just give some examples now. This is a long-term trial in the highlands of Kenya, 18-year trial. And this is the improvement in soil carbon, kilograms per hectare per year over the 18 years. They had a multifactorial trial with fertilizer, fertilizer NPK, plus or minus, stover return or not, plus or minus, and then cattle manure, plus or minus. Just the major points here, you don't need to look at the type, just look at the total soil carbon change. You'll see adding everything gets you the most, not surprising. In this case, just fertilizer, there's still a decrease compared to what it was. Stover return by itself does quite a bit. Manure, well, we don't have the manure by itself there. But anyway, so various combinations. Oh, is there? Sorry, I can't see. Okay. Manure does better than stover. Manure is well known to do much more carbon sequestration in soils compared to crop residues and things like that. It has a lot to do with the quality of that organic material. It's already passed through a cow, so all the labile carbon is gone, so it really builds up much faster. The point is, look, it's only 300 kilograms per hectare per year. And these are on highly productive clay soils with good rainfall. And so that's quite little compared to some numbers we see for carbon sequestration in the tropics. Another example, this is improved tree fallows just after 18 months on 2 soil types. This is in western Kenya. There are poorer soils. This is soil carbon content, milligrams of carbon per gram of soil. Continuous maize. You plant Tephrosia, it's a legume fallow. 18 months later, there's quite a large carbon sequestration in that soil. But at 18 months, you cut that, and you go back to maize. So this would be sort of a maximum. It would probably increase if you had continued applications. But there are no data on carbon changes through rotations of legume tree fallows, maize, legume tree fallows. This is just after one growth. We don't really know the long-term trajectory for carbon. 2 miles away, the same trial, a different legume fallow, but on a sandy soil. Much less carbon is sequestered in that amount of time. So again, it's important to know the kind of soil and the management you use to be able to determine how much carbon. Just another one, continuous maize. This is full fertilization. This is in western Kenya. You'll see in this case, compared to the other one, that full fertilization actually increases soil carbon. It's because it's getting roots back into the system and such. So in some cases, you won't have increases with fertilization, and others we're finding it. And it's not the stover management. It was the same here. So again, it depends on the soil, where it is in the degradation. And then here are 2 different legumes. Again, or here's a legume and here's a non-legume. Here, these are numbers you find quoted quite often, 3 to 2 tons of carbon per hectare. So we have a lot of trials giving very different numbers on very different soil types, but there is not enough information long-term for us to really know the amount of carbon we can sequester in the long term in these systems. They're all increasing crop yields, so it's a plus. The more carbon we get, the better, but they're all increasing crop yields significantly. All right, adoption rates. As Pedro mentioned the other day, here's a legume fallow, here's biomass transfer. So they worked, ICRAF, the International Center for Research in Agroforestry, worked for about 10 years with, I would say, probably 1,000 farmers or so And 10 years later, they picked 120 random farmers out of those pilot farmers to see what happened. Were they adopting it? And did they continue it? Well, here you see only 27% of those farmers were doing it 5 years later. And it goes up, it goes down, but it's only around 30%. Biomass transfer, very similar, it gets a little bit higher. So it's not huge adoption, and these are people you work with intensively, okay? It's not just mass extension, it's working with individual farmers, and you're still finding rather low rates of adoption. The other thing is it's on a very small area of their farm. Less than 10% of their cropped area are they putting under these improved techniques. These are farmers that were given the inputs, provided all the extension you can imagine, and they're still not adopting to a large scale. One of the major things is the labor requirements in a labor-scarce environment. The other one is land requirements for improved fallows or even cover crops. These are areas where farms are less than a half a hectare, acre-sized farms or less. And to have to put part of your farm under something that's not growing a crop, farmers aren't willing to do it. You also have to forfeit a season, a cropping season. So there are all sorts of reasons why farmers might not adopt this. And in some areas, there are land tenure issues. Women can't plant trees, so they're not likely to plant trees on. So you have to think it's not just a technology. We know you can get carbon in the soil, but farmers aren't doing it. Selected farmers with which people worked a lot. Here's a case in Zambia, and this is again 10 years later. They worked with many more farmers there. You'll see this is a wealth category of farmers, reasonably well off. Again, it's probably less than $2 a day to very poor farmers. And you look at different management practices that they are practicing after being taught many of these crop rotations, crawl manure, that's cow manure, mineral fertilizer, and improved fallows. You see they're much higher in Zambia. They're higher, the wealthier categories. The farms are much bigger in Zambia than they are in Kenya. So you remove some of those constraints to adoption and you do find adoption. So it's not like it doesn't happen, but you really have to look at what are the conditions upon which people could adopt these practices. So just a few points to make. The rehabilitation of degraded agricultural lands results in increased labor demand and increased capital inputs. You don't get anything for free, okay? People say there's all these degraded lands in Africa, let's just rehabilitate them. Well, it takes money, it takes labor, it takes inputs of all different kinds. So it does cost to rehabilitate. And it requires nutrients and carbon in most cases. The soils are poor. They won't grow biomass without added nutrients. And then very little time has been put into what are these social systems, institutions, and incentives that need to be in place so that people can adopt these carbon sequestering practices. Now, I'm just going to briefly talk about land outside of croplands, because that's also a large part of Africa, and this is perhaps where biofuels should be focused. And so this is generally trees, reforestation on degraded lands that aren't being used for crops. So in Ethiopia, there are huge examples of what they call set-aside or enclosure areas. There's been such massive erosion, there is no topsoil. It's because of grazing and fuelwood collection. And they're really finding, if they set aside these areas, either with a physical fence or a social fence that are guarded by the local people, that within 2 or 3 years you actually find native vegetation and grasses coming up very quickly in areas you would not think anything would grow. If you do it with enrichment plantings, it grows even faster. Woodlots. Fuelwood collection is the first thing to start degrading a lot of these lands. You expose the soils. I think a lot can be done in terms of planting plantations. Even eucalyptus. Everybody says, oh, I don't say eucalyptus. But it does grow very quickly. It can get carbon in the soil. But you have to look, what is the best tree, again, for that climate, for that soil type. And then biofuels, I'm just going to make a couple of points. One, it cannot compete with food production or grazing systems in Africa. And we must not assume that these degraded open lands are not being used by people. Very often it's said, oh, we have all these degraded lands, let's just go. But a lot of them are being used by communally, not used well perhaps, but it doesn't mean you can just go replace them with biofuel plantations. So really let's think of the social aspects of biofuels. And Rattan, I think, will back me up on this. People are saying, let's just put jatropha all over these semi-arid lands. Well, there have been no systematic studies done of how quickly jatropha can grow on a wide variety of soils and climate types. In degraded lands and semi-arid tropics, they're going to grow very, very slowly. So carbon will build up very slowly. Biofuels will be available at a very low production level, unless you add water and fertilizers. So just some major points I want to make. I think the discussion's just started. We need to look at this a lot more, look at the soils, climate, and where the people are, and where the food needs to be grown. And if we can feed the people, as David Tillman said yesterday, probably if Africa does double and triple, we can keep the crop area we're using. And some of these degraded sites, we could do other things for fuel wood and biofuels. So just to pose a couple more questions, I'm almost finished. Rattan showed the Glassod estimates, and Glassod was expert opinion more than anything about all these degraded lands by different types of degradation. I don't want to use those numbers because I don't want to keep proliferating something that's not good data. But anyway, so we don't really know where these degraded lands are by these different types of degradation. We don't know how extensive they are. Like I said, some are combined, water erosion, chemical degradation. And we still don't know what is the best management strategy for rehabilitation of those different combinations of degraded lands. I'll just briefly talk about a project that's being funded by the Bill and Melinda Gates Foundation. It's a digital soil map of the world, and it's to get high-resolution, 90-meter resolution information about soils and covariates, climate, topography, geology. So we know more about the soils, and there's a particular, it's just putting covariates together so you can find out more about soils, and it's then used, what are the best management recommendations? Peter and I can tell you a lot more later, but I just wanted to say there's a particular focus on Africa that has had very few soil samples. Some people say, and it's true, we know more about the soils of Mars than we knew about the soils of Africa. The whole Congo Basin has been mapped 2 soil types with 1 soil profile. So there is a large effort underway to systematically sample various soil climate types in Africa to get better information. And they're called sentinel sites. This is 10 by 10 meter, 10 by 10 kilometers, randomly selected Landsat images, and then randomly selected spots. You'll get more on soil, land cover. We'll be able to look at the degradation, the type of degradation, why it's happening, the extent of soil carbon losses, and all of that. With the intent in the end to really figure out what is soil carbon in Africa or other places. Right now, the FAO soils map, the soils were collected in the 50s and the 60s. And probably the soil carbon has dropped 50% in most of those places. So it's to get an up-to-date and a repeatable soil map using very modern and rapid techniques. This is just an example. So here's sort of a global use. As Pedro said, it can be used for modelers. A lot of people would probably like to use this at global scales or regional scales. But due to the high resolution, then you can actually look. This is a degraded woodland in Mali. And what this is, it's topsoil carbon deficit in these red areas. All right, so you could figure out where in the landscape you really need to manage where you could increase soil carbon. So we hope with this digital soil map, we hope in 4 years we have the first version of it. We'll have a better way to find out where the degraded soils are, how much carbon they've lost, and then really alongside this we're doing management trials at each of the sentinel sites to figure out what are the better ways to improve yields in a cost-effective way, but also look at carbon sequestration. So that's all I have to say. Thank you very much.
But before we do that, let's just get a little question going. Dr. Wallen, you come on up and why don't you
there, Cheryl. So I want to ask two questions, two categories of questions. Why don't you have a seat? First, Cheryl, how do we do it? You presented the challenges on Africa. The first question is, what should we be doing? How could we create the support systems, the incentives? How expensive would it be to do accomplish a meaningful amount of what Dr. Lal had talked about as the potential?
Well, I think the first step, is this on?
No, come on up here.
Can you hear me all right? Oh,
yeah.
Anyway, the first step is underway, and Pedro talked about it with the African Green Revolution, getting chemical mineral fertilizers into the soil to jumpstart this whole thing so they become productive. Even just growing a crop, returning residues with the roots, you start building soil organic matter that way. So we could already calculate what that is costing just to build it up there. But to get it to the next bigger step, you've got to have some of these cover crops. People will not be able to afford mineral fertilizers, so we have to transition to an integrated system. Some far from roads and markets will be more organic than ones that are closer to markets. They'll be more. So the balance is going to be quite different. But again, how to get farmers to accept it? They're going to have incentives. They're going to have payments. The numbers I've seen for the price of carbon, $25 per ton of carbon, that's a high one. But if you look at many of these are less than a ton of carbon per hectare. Much of that money will go to monitoring, so a farmer ends up with what? $10. They're not going to do it for $10. I think we have to think of co-benefits, fuel wood savings, and energy efficient stoves. So people are trying to bundle different carbon products to see if that can get you there. But I'm doubtful. There have been no small-scale farmer carbon offset project yet in Africa because of these difficulties.
Tim, just a quick question to follow up with Cheryl. Has anyone calculated just the nitrogen costs for storing a ton of carbon in the soil? Is there a good rule of thumb? Because nitrogen's getting pretty expensive.
Bobby Stewart and I had a paper on that. Bobby Stewart from Pennsylvania. We talked about 1 gigaton of carbon sequestration, and you approximately need 1/15th of nitrogen of that amount to. You mentioned yesterday carbon nitrogen ratio of 1/15. That nitrogen has to come from somewhere. You need 1/50th of that amount in phosphorus. You need 1/500th of that amount in sulfur. Those nutrients must come from somewhere. We conducted an experiment. This is private, and I worked in Africa for 20 years.
Good, perfect.
From Nigeria. And your question, I really agree with what Sarah said. But one thing that we did find out initially when we started work in West Africa was there's so much known going back to 30s. Belgian Congo had 23 experiment stations called ENIAC throughout Congo and Zaire. When they left in 1960, they published a book called Primitive Farming Modernized. The data on mulch farming, the data on different cover crops, the alley cropping that we think we discovered agroforestry in the 80s, they call it the corridor system. There was excellent work done on the tide bridges and so forth. Rounds published in 1935. That is Greenland book in 1958, and so the carbon modeling was really naive in Greenland in 1958. Look at Nami Hudson's work in Zimbabwe when Zimbabwe was still a good place, which was a classic work, why erosion happened. The question is why such a great information existed but nobody loved it. That's the important part of it. And that's why the very first day I mentioned that day that the socio-economic, the policy, willpower to do something. That's why I was very happy to hear Pedro say the other day, the Prime Minister from Zambia, who said, I will put my money into it. That's what we need. somebody willing to say, I'll put my money.
Let's have a couple more. Why don't we take a couple questions at the same time? Hidden and involved, and then.
I was actually wondering if you can speak to the mic when you answer my question. You mentioned in one of your slides 25 years, which makes sense as the residence time for stored carbon. Is it not true that whatever it can take up, if it's 114 ppm or if it's 120 or 100, is it not true that this is merely a transient, and once you max it out, that's it, the d by dt is zero from there on, whereas we're still pumping, okay, so maybe it'll drop to half the rate now. We're still going to pump CO2 into the atmosphere. Is it not true?
No, it's not. That is a misconception. And that is where many times people have said, we do not want to have Article 3.3 revived to improve soil carbon, but it's not permanent. Mean residence time is a mean residence time. It's a mean. It's like a mean age of this house here is 25 years, and there will be nobody at 25 years age. Soil carbon, we have monitored in soils, some soils in Africa also using delta C13 signature. It can be thousands of years, 5,000 years, 10,000. The recalcitrant carbon. The transient carbon may be just a few months old. So it depends on, that's why I specifically showed the formation of organomineral complexes. When the carbon was interacting with clay, as Sharon said, that carbon is gone forever.
Well, what's the weighted PDF? What's the weighted PDF of the update?
Meaning the residence time?
Yeah.
Weighted average?
Yeah, you have a PDF.
You have to actually monitor the pool of the flux. That's the only way to find that out, the exact number of a given spot in time. Or you use delta C13 signature and calculate that. But you cannot say that the soil carbon is not permanent, because that is a misconception.
I don't think that was the question.
Well, let's share.
I didn't say that it's not permanent. I said you get one shot at it. That's it.
So I think the question is, and both for Tam and I brought it up, is how much soil carbon you lost, which gives you a potential for how much you can put back. But rarely do people ever get back up to that potential. But it does saturate. These rates are all from recent experiments.
Yeah.
And
It does saturate.
It does saturate.
25 to 50,
Yeah.
yeah.
They've shown in some manure trials you can get above potential, but very few of that. So yeah, it will saturate.
25 to 50.
We don't know enough about that saturation yet and how long it takes in different systems.
Walt and Denise that are in. And then
my question is really for both of you is about the cost of monitoring, particularly when you think about the potential for incentive payments that might be linked to a carbon market, and sort of thinking of an individual farmer potentially getting incentive payments. How costly is it to actually monitor soil carbon where you have some confidence of what's there, like how much effort does that require, and then how much of a wild card, and on that point I think there is a consensus that one has to actually look at performance rather than just a change in practice. But since that would come from a change in practice that may have implications for example, nitrous oxide emissions, how much of a wild card are other changes beyond soil carbon? Do we have any capability within the next 5 or 10 years to have some confidence about what the net change in emissions might be for that change in practice?
And let me expand on that question. And then, Michael, I'm going to distract you from whatever you're doing because I want you to help participate in this answer too, if we can distract you back in a second. One guy, Chris Pichard at the University of Wisconsin, who does a lot of soil carbon on CRP lands and other lands. I don't trust any soil carbon numbers because I work so hard to get accurate soil carbon from a single field. And I just don't trust most other people's numbers because they get the number of sampling they're doing is a lot smaller. So on one hand you have the Chris Pichard rule, and then Michael was giving me a view last night about the potential, and well, I'll call on you later. So why don't you guys address this issue? Are we doing new technology to let us do this cheaper?
Yeah, if I could just start. And the digital soil map is putting these new technologies to play. There's near-infrared technologies now. And the group working with us, Marcus Walsh and Keith Shepard in Africa, they now have I think, 50,000 soils from Africa where they've done both the carbon in the lab and using near-infrared, and you can do it with near-infrared 99% for our soil. And so you can do lots and lots of soil carbon. What they're also trying now to do is in these quick grid image and satellite images is looking how can you also do it at a landscape level by the reflectance from the soils and near-infrared. So they're...
And that's down to a meter or more in depth?
No, it's surface soil, but I think with the digital soil map, we will also know about depths, bulk densities, and things like that. So it's these covariates. Well, it's a lot of modeling, but there's also uncertainties that we can put behind those numbers. And anyway, I think you could get there.
The commercial price in Ohio and other labs is $15 sample of carbon and nitrogen together. These people make money on that. My analysis cost where I do and I transfer from one budget to another budget is $4. And that does not include the cost of reading my CN analyzer. There are new techniques. One important one that I have calibrated for Brookhaven National Lab is what's called inelastic neutron scattering. It's a tractor-mounted equipment, and it monitors the carbon pool to half a meter to 60 centimeter depth in megagram per hectare. When you drive over the landscape from the top of the hill to the valley bottom, say 5 miles per hour speed. When will that become operational? I do not know. Lucian Milopolsky is the one who is designer of that at Brookhaven. So there are technologies such as that available. But what I want to mention is this. CRP, for which we have been paying for 40 million acres under CRP for the last 20 years, did anybody ever take a flume out to monitor whether the set-aside land had a runoff and erosion control or not? It was assumed that when you take land out of production and let it go back to forage, it did whatever it was supposed to do. So, on the basis of that, supposing whether it's a no-till farming or cover crop or agroforestry or whatever, we find that around Machakos, the area rate of carbon sequestration what Cheryl presented was 1 ton per hectare. It's 1 ton per hectare. That is how you have to implement the trading scheme. And then take a discount of uncertainty on that 5%. You can never take an auger out on each acre and say, that will be it.
So that's going to be a big policy question.
Jerry has. I think Jerry's talking about that.
Well, I wanted to Dave.
I just wanted to clarify. The soil carbon stock estimates and the monitoring has 2 parts: carbon concentration and bulk density. And it's the bulk density part of the problem that is really the difficult part of the problem and creates the expense that Walt was trying to get at. And so, I don't know how, with remote sensing, you're going to deal with the bulk density part of the problem, but that's 90% of the issue.
That's where the inelastic technique I mentioned to you takes care of it. It monitors stock.
Denise and Dave both, and then we'll... No, you're not allowed to answer until we get both questions out.
I've read things written by EPA and NGOs indicate that biochar might be the answer for getting carbon into the soil. Can you comment on whether this is something that's just pie in the sky?
I'm going to ask you to hold that. We're going to have a presentation on biochar. Debbie is sort of through that. So we'll hold that question. We're going to have a whole discussion of biochar. Dave.
I guess having looked at a variety, 50-some fields around the 5-state area around Minnesota, North South Dakota, Iowa, Wisconsin, and looked at carbon dynamics in them, there is a huge effect of the species composition that's growing there. And one thing that we've seen is that the mixtures which have cool season legumes and warm season grasses store much more carbon, 2 to 4 times more carbon than ones which have just one or the other of those. And we first discovered that when we looked inside of a 20-year deer exclosure experiment we had set up at our site. And without deer, a native legume, Lathus venosus, became incredibly abundant in the spring. But it would die and dry away in the middle of the summer. But its nitrogen allowed the C4 grasses to grow. And in that period, in a stand of native savanna, had never been farmed, never been plowed, native vegetation, the total carbon in the soil doubled over that 20-some year period. We have a couple of papers out on this. And it really was a shift in composition. So I think that there's a lot of room for wiser management of grassland vegetation to maximize the rate of storage of carbon. And that also suggests, Cheryl, from what you said, that yes, on average, we expect native vegetation to take soils back to what they were. But if there were things like herbivores keeping legumes at low abundance, for our work suggests you might actually be able to go quite a bit higher than the carbon had been in that soil if you don't have those herbivores present in the restored land.
Actually, this is very interesting. There's some new articles out suggesting, finding that New Zealand grazing lands have lost a tremendous amount of carbon, which is a real concern because you tend to think of New Zealand as having the best managed grazing lands in the world. And I'm wondering if some of the grazing and renewables would be part of it. I have a question. Last question here. Do you guys have a comment?
Paperwork at CIAT, and CIAT had article that you shared. They were evaluating under green grass, and I had a student who worked there, and we had done similar experiments in Nigeria on green grass, Panica maximum, which had very, very high rates of carbon sequestration, both in the below ground and above ground. In fact, the data that CIAT published was 10 tons per hectare of both. I have compared to green grass data with switchgrass in our biotechnology site. There is no comparison. Switchgrass is very, very small compared to that. Green grass, elephant grass is the same thing. Some of the tropical grasses, elephant grass, green molasses grass, are very, very important in the stability. If you can do it in tropical savanna, we can quite well.
Can I just ask the second part of this question? If you do convert to these more intensive systems with fertilizers and even legumes, we all already also know that they also give off nitrous oxide. I haven't looked at the net budget. They were probably higher in terms of net greenhouse gas emissions. But I think we have to then look at is there other land that then becomes recuperated without cropping. And I think that's the way you have to look at it. You have to have food security, and I don't think you can do it without fertilizers that will increase nitrous oxides. I don't know the balance between the carbon stored and nitrous oxide. That should be a fairly easy.
I'm with you. Now we're gonna cut this off for the moment to have a quick presentation on biochar. We will go from that to get our coffee break because they're going to take stuff away at 11, and then we will come back and have more of this discussion.